Thank you. Well, it's really nice to be here in Krakow. It's nearly 10 years since my last trip. More to the point, it's over 2 years since I last left Britain, so it's a very welcome change to actually be able to travel internationally again. Thanks for the invitation. So when Agnieszka asked me to speak, she didn't say what about. So I decided I would speak about the thing I'm most enthusiastic about, because I feel that the lensing of the microwave background is probably the area of cosmology that's poised to make the biggest leap in what it tells us about the universe over just the next year or so. So it's a very exciting time for this field, and I want to try to give you an overview of it, starting right from basics. Good. So So we're in a great position in cosmology that we have a standard model of structure formation that more or less works. It allows us to connect initial conditions, fluctuations, in metric, see at redshift of 1100 in the cosmic microwave background with the structure that exists around us in the galaxy distribution today, which is just a few tenths or less. What's become interesting over recent years is that it used to be said that the cosmic microwave background gave you a very pure, clean probe of the high redshift universe. But in detail, that's not true. What we've seen is that, of course, the large-scale structure is developing all the way. The photons are traveling from the microwave background back to us. And so those metric fluctuations in intervening space are able to imprint themselves on the microwave background and introduce additional signals. Those extra signals could be seen as a nuisance, but they also contain essential cosmological information that's hard to get any other way. So actually, they're a good thing. So let me just review briefly the three main ways in which intervening cosmological structure affects the microwave background. Two of them I won't really say anything about, but just for completeness, let's list them. On the larger standard scales, microwave background contains additional effects from the integrated Sachs-Wolf effect. And this corresponds to a probe whether the gravitational potential phi is changing with time. So you can imagine some static gravitational potential well, the photon falls in, gains energy, goes out, loses energy again, nothing changes. But if the potential well is evolving during that time, there's a net change in the photon energy. And so that imprints additional temperature perturbations on the microwave sky. As I said, these are gravitational potential effects. The gravitational potential is always important on large cosmological scales. And so large angular fluctuations in the CMB are influenced in this way. Alternatively, on small scales, the most important foreground is what's called the Sunyaev-Zel'dovich effect, which is basically the impact of Compton scattering. So, ionized gas takes an input photon, scatters it, and the angle of scattering changes the photon wavelength if the electron is moving. It can be moving for two reasons. Either the plasma is in bulk motion, and after all, cosmic structure formation has to be associated with a peculiar velocity field. So you then get what's called the kinetics, Sunyaev-Zel'dovich effect, KSZ, which is just proportional to the line of sight component to that velocity field. But the standard thermal Sunyaev-Zel'dovich effect comes from the fact that the scattering gas is hot, so the random motions of the scattering electrons, and those velocities imprint themselves as well. So as I said, on scales of, let me say, arc minutes or below, the SZ effect is very important. But in between the SZ effect and ISW is what I want to talk about in these lectures. And that's the impact of gravitational lensing. Hanslock, who's now considered themselves an expert in gravitational lensing, having had 3 lectures on it. Yes. Well, okay. It's the second go around, but it's gravitational lensing, which is recycling the same sort of technology that you heard about from Cosmology, looking at distortions of galaxy shapes that will be studied by Euclid and so on. But this is the impact of that same phenomenon of distorted photon trajectories from the microwave background to us. And so they distort the CMB sky. And it's those distortions that CMB lensing is all about, exploiting that signature. All right, what does it look like? So here's a simulated patch of an ideal little portion of the cosmic microwave background, showing a fluctuating radiation temperature. It's not a big patch, it's only just 6 arc minutes across. If we superimpose, at best case, the realization of foreground large-scale structure, it turns into this. So you can tell the difference, right? The most apparent thing, these octopus suckers, which are Einstein rings, and that tells you that sitting at this location is probably a rich cluster of galaxies of mass 10 to the 15 solar masses. And there's lots of these things all over the place. So the basic excitement about this field is that your intuition tells you, just looking at this picture, that because your eye can see that structure, it ought to be possible to make a map, an objective map, with the projection of the density fluctuations between us and the microwave. And that's exactly where the excitement is. And as I said, I believe that this has already delivered really novel and exciting cosmological constraints. It's poised to go up an order of magnitude in precision, really by the end of this year. So this is absolutely the right time to pay attention to this field. But although it's new, and finally, it's also quite old. The basic method of making this work was solved by Wayne Hu back in 2001. There's a wonderful review article by Anthony Lewis and Anthony Chalmers in 2006 that basically unpicked in detail a rather short paper that Wayne produced. Up till now, this method of finding the foreground large-scale structure from microwave background has been applied with great success to data from the Planck satellite. And the most recent number of iterations of that was a paper by Julian and Caroline et al. Just came out a month or so ago. If you want to look at the details. All right, well, that all sounds great, but what are we going to do exactly? What's the algorithm? What's the approach? Now, I have a choice here. I could just say, well, you can see roughly how it would work. Never mind the details, let's just look at the answers. But I decided that I would take the title of this meeting literally. It's a Cosmology School. So I'm going to try to go through this in a pedagogical way and actually give you a derivation, because I think it's really, really clever the way this is made to work. And it has the advantage that it exercises a lot of statistical tools that we have to use in many areas of cosmology, working with microwave background, intrinsic fluctuations, working with galaxy clustering, anything to do with correlation functions, power spectra. There's a common set of manipulative tools. So a lot of you should be interested in the details of this. If you're not, or even if you are, but you're tired, because I know it's the end of the day, and it'd be better if this was fresh in the morning and we're all energetic and ready to go, right? Nonetheless, I'm going to have a go at giving you an outline, a relatively detailed outline of how this all works. Alternatively, you could just close your eyes for 10 or 15 minutes, and then I'll get back to show you some pictures of the results, okay? But let's see what we can do. I encourage you, not just for this, but actually throughout all the lectures that I'll be giving, to stick your hand up or just shout out if you've got a question, if you want to clarify something. I'd much rather, it became clear that there was something that wasn't clear now than in an hour and a half's time. All right, do we have a deal? Good. Okay, so various bits of definitions I may as well talk about. Delta will appear a lot. It is the fractional fluctuation in the density away from uniformity. Okay, so delta equals 0.01 means 1% denser than average. Almost everything that we do in vascular structure makes heavy use of Fourier analysis. So, for example, you can think of representing this fluctuating density field, call this the density field, although it's the fraction density perturbation field, as a superposition of plane waves. There's some amplitude, is a function of wave number, plane wave into it. We talk a lot about the power spectrum as a characterization with these random fluctuations. And that's because if you just take this and square it to work out the variance in the density, it's rather easy to show. I'll say more about this shortly. But that's just the sum of the modulus squared of his amplitudes. And that modulus squared is the power spectrum. Although often it will be convenient to talk about the power spectrum in a different notation, which you will see characterized as big delta squared. And what this is the contribution to the overall variance that comes not from a single mode, but comes from some logarithmic range of wavelengths. It's actually, that conversion gives you an extra power of k cubed. Anyway, so that, if you see a big delta squared, that's the power spectrum. It's saying how the variance in the density is dissected according to the scale. The other thing that we see a lot is the two-point correlation function, phi of r. That is the average of delta times itself offsetted by some value r. That's the autocorrelation. Now, does everybody know what these angle brackets mean? Yes.
That's an envelope.
It's good. They are the ensemble average. What does that mean? The density field has got some random fluctuation, which may have come from inflation or some other theory yet to be invented. And the point is, it's a random process, like waves on the surface of the sea. Somebody, to make this, has been throwing random numbers. If it's inflation, quantum mechanical random numbers. But you can imagine repeating the experiment, generating a new set. So all these Fourier modes might have some different effects, for example. So when you see angle brackets, unless otherwise said, that means you're just considering multiple copies of that probability distribution. Okay. Now, I gave you an informal definition of the power spectrum just then, but there's a more formal one that people often see. It's this red box here. What is it? It is the Fourier space analog of the correlation function. That is, it's take a Fourier mode at one wave number, take a Fourier mode at another wave number, and ask if those two are correlated. And the textbook expression says that they are not, unless it's the same wave number. This is a delta function in Fourier space. The magnitude of that delta function is the power spectrum. So, who's not seen this equation before? Wow, very good. Nonetheless, I'm going to say a bit about it because it's absolutely critical to CMB Lensing. Because this is a very general relation. It applies, you say, for a statistically homogeneous random process. So homogeneous means the same in every space. Okay, I can tell you something useful in this field. Sometimes you'll see people, usually Americans, say homogeneous. Yeah. Do any of you say that? If you do, don't, because there are two words which are different, homogeneous and homogeneous. Homogeneous is a biology term, meaning having the same genes. Homogeneous is what we use in cosmology. It means the same everywhere. So it means that the correlation properties of the field don't depend on position. You know? Something here, something different. All right. So let's talk about how one would actually prove this, because a lot of the manipulations needed to be convinced this is true are what you also need in CMB lensing. There's a problem when you're working with large-scale structure and you want to do Fourier analysis, which is the universe is infinite, which, when you want to do Fourier transforms, that's the density field, presents a real problem of whether the integrals that you're doing are going to converge. So a better way of doing it, which I certainly prefer, is to be explicit about the facts. You're not going to go to infinity immediately, but rather what you'll do is content yourself with doing Fourier analysis in a part of the universe that's of a finite volume. So there are lights, I guess you can see this. So I'm going to construct my universe by periodic replicas, some fundamental box of side L, and in due course it will go to infinity. But if it's not finite, then nothing is well defined. So you should really think that the density field is a superposition over wavemodes with finite amplitudes, and it's a sum because there are only certain allowed values of the wave number, is the ones that satisfy the condition of being periodic. So there's multiples of this fundamental wave number 2 pi on L. Later on, you are getting lectures on n-body simulations. That's right, yeah? Well, n-body simulations are really this. You only work within a single volume, and yet a lot of Fourier technology is used, and you have to do a bay, and you have to take account of what the fundamental mode is.
Yes, indeed, John, I really appreciate that you're saving me some time.
Okay, good. But, however, as we know, well, okay, as you can see, as the box gets bigger, the mode separation gets finer. And in the limit, you can replace this sum by an integral over wave number space with the density of states, exactly the same density of states that we use in statistical mechanics. I think you've seen this before, V on 2 pi cubed. Just comes from that fundamental mode spacing. Okay, and the invert Fourier relation is you want to find this thing. So you multiply by the complex conjugate wave and integrate. And you're integrating over the volume with modes that make a whole number of oscillations. So anything that oscillates once has an average value of 0. So the only determinants that survive in that integral are the ones where this k cancels that k. So you pull out the wave number of interest, and you're integrating a constant over the box, so you better divide by v. Yeah. You often, in cosmology papers, don't see this v appear at all, which I think, in terms of understanding what's going on, is a great shame. People just effectively pick units where v equals 1. Or actually absorb it into the definition of the amplitude. But when I'm deriving things, I feel happier putting it in, because if all the v's disappear at the end, I know I haven't good. Well, not that. All right, so these things can look much more intimidating than they really are. So let me try to persuade you. So this is just the derivative. This is just the derivation of our 2-point function in Fourier space, showing that it's the there's the delta function. So let's build it up. We need to multiply two Fourier amplitudes. Okay, I'll do it backwards. So first of all, we'll build up the correlation function, multiply two fields. That's just multiply together two Fourier sums of our involves two different wave numbers. And the correlation function, well, I said normally angle brackets mean the ensemble average, but actually you can, if you've only got one data set, you can still estimate the correlation. In fact, we can't estimate the ensemble average, of course, because we only have one member of the ensemble. So this is something that very often we do, almost without speaking, in the statistics of large-scale structure, is that we take a volume average, over the volume, and assume that for a large enough volume, that's going to tend to the ensemble average. And that property of statistical process is called ergodicity. All right, so if you perform that volume average over this product, then as usual, anything that oscillates averages to zero. So that forces the k and k prime to be the same, and you end up summing over the wave number, and you get the usual relation. The correlation function is the transform of the spectrum. And as before, our spectrum is 1 over the volume times the spatial integral of the correlation function. Its oscillation. All right, so now so we have that same relation in the previous slide relating delta in Fourier space to delta in real space here. So let's write that down twice, multiply it together. 1 over v becomes 1 over v squared. We've got two integrals now, two densities, two exponentials integrating over the two spaces. All right, so now comes the critical step in this argument. I want to take the ensemble average. I need that down here. I'm taking the ensemble average of something that's got two deltas inside. So I can be after me on the slides. I guess those will be online. Okay, so you've got two deltas inside here. Everything else is just functions of position. So the ensemble average comes in around this term and sends it directly into the correlation. And because the field is assumed to be statistically homogeneous, that means the correlations are translationally invariant. The x dependence disappears and we just have a function of r. So this is the critical thing. And this is what you can see is going to be broken with CMB Lensing. Because if you can make many realizations of the microwave sky, coupling ensemble, if you stick a single gravitational lens in front of each of those ensembles, that's broken this translation invariance. Yeah, is that clear? So, ensemble average, you only get translation invariance in gravitational lensing if you change the CMB sky and the foreground structure each time. But we don't. What we're interested in is the impact of specific dark matter blobs on the background CMB, averaging over the statistics of the CMB, because we don't know what they are. All right. So we have a correlation function in here. And we know that right, now x has disappeared. So I can integrate over x and get 1 power volume, so v squared becomes v. And I just have the correlation function Fourier transform, which we define as the power spectrum. And that relation, where do we start? The ensemble average of delta k times delta k prime is the power spectrum only at k equals k prime. Because remember, the notice is distinct. So how do I get a delta function function. Can you see the board, by the way? Because I could put lights on. We have individual points, case space. We've got fundamental node separation 2 pi 1L. So if I want to integrate my thing, which is a constant, when the modes are the same, that's effectively just integrating over the fundamental square. It's governed by one mode, or the cube in 3D. So the volume integral will be whatever this thing is, which is the power, times the k-space volume of the single cell, which is 2 pi cubed on V. So you put all that together, finally, in the limit that V becomes large, that top hat becomes a representation of a delta function. So you can see in the continuum limit, yes, you have a delta function in Fourier space. The 2 pi cubed is understood because it's the fundamental mode, although in 2 dimensions, as we will be from microwave sky, that 2 pi cubed is of course 2 pi squared, or the dimensions you have. And the V's have been distributed here. So henceforth, V is going to disappear from my lectures because I'm trying to make a connection with all the literature you can read on this. But whenever people talk about the power spectrum, what they really mean is the power spectrum times the normalization volume. The power spectrum is dimensionless, but V isn't. And so in the literature, the power spectrum has dimensions of the volume, and this is why. And Fourier components of the density field actually have dimensions of reciprocal volume. That's something, a volume also in the literature to absorb this t squared. All right. Are we all right? I encourage any questions on this. I can sort of understand, you get the vague idea. Distinction between volume and ensemble averages, using this idea that the mode is averaged to 0 if they're oscillating over a fundamental volume. All right, last chance. Well, not last chance, shout out at any time. All right, so let's apply some of this to gravitational lensing. So here I think is something that I think would have showed you, roughly. So the usual sort of geometry one sketches is some deflector, true source here, light is bent by some angle alpha. So you, the observer, believe the source is over here, it's over there. So theta I, the image angle, is different from theta source angle. And the standard lensing equation says that the difference between these angles, which is this bit, proportional to the bend angle, is written as the angular gradient of a lensing potential psi. That lensing potential is proportional with some distance dependent kernel to the line integral gravitational potential. So when I say line integral, dl is an element of proper distance followed along the line plane. That lensing potential obeys a Pascal equation, a two-dimensional angular del squared. I mean, subsequently I won't have this theta on here, but I'm just trying to emphasize that usually this is done in angular units. Everything we're talking about is in radians on the sky. Megapascals. That was the right-hand side, which is twice kappa. Kappa is the convergence. Here's an expression again, it's proportional to the line of sight integral of the density, well, the density fluctuation should be a delta rho in there. And kappa is a really nice number because it delineates whether the gravitational lensing you're talking about is large or small. If it's small, then the sky is weakly perturbed, galaxies change their shape by an amount that's of order kappa. And so actually, with galaxy lensing, which is what we talked about, the typical, well, does anybody remember, what's the typical ellipticity introduced by galaxies, gravitational lensing in galaxies? Come on, 10 to the minus 5, 0.1. Don't remember. Well, it's about 1%. Okay, so gravitational lensing, if they take a typical galaxy, which is 1, that could be precisely circular, and make it something with an ellipticity of 0.01. Okay? And indeed, on the contrary, if kappa is unity, then you get strong lensing. So without knowing anything, you know that along that location in the sky, kappa is of order unity. So we're going to make maps of kappa. That's what CMB lensing is all about. Okay, but I have bad news, which is that somehow there's been a development. The people who worked on gravitational lensing from the point of view of galaxies, have used different sign conventions from the CMB lensing people. So here's what CMB lensing looks like. It's negative sign convention. So the apparent position in the sky, so x now, it's a vector, but it's to be thought of as the angular location on the two-dimensional sky. So this is a two-dimensional coordinate that lives in the sky. What exactly that means if on the curved sky is maybe complicated. So for most of what I'm going to be talking about, you will imagine that we have a sky is flat. So we're just isolating some portion of the sky, putting Cartesian coordinates on that little square. And all the interest in the data lives on angular scales of of order degrees. So this kind of flat sky observation, this is perfectly fine. All right. Gravitational lensing. Its impact on the objects that are being distorted depends on one critical thing, which you wanted to be fancy, you would call Newton's theorem. If you wanted to be unfancy, you're an astronomer, you could talk about surface brightness. Everyone knows about surface brightness, yes? And you know that it's independent of distance, for example, modulo cosmological redshifting. So gravitational lensing can service that. It alters where you think a photon's coming from. It doesn't change the surface brightness of what you're looking at. So that is, the CMB temperature is preserved along the photon ray, whether it's translated or not. Happy with that? So that means I can express, no, it's far too eager. So I can express the temperature that I actually see. I want the temperature at some observed location x. Well, that x came from some true location. So that true location is the x that I actually observed plus this graph item. So the observed temperature is temperature field, the true temperature field at the location of wherever I'm interested in, plus grad psi. If I take a continuous image of that, so everything in CMB lensing relies on the assumption that the gravitational distortion is weak. To the first order, that adds an additional term which is the scalar product, the gradient of the temperature field. Gradient, I just mean, in this sense, P is some field that lives in this square. It has a two-dimensional gradient vector in that square that's pointing in some direction along the plane of the sky. And that's dot producted with the gradient of psi. So what we're going to try and do is produce a statistical procedure that uses the existence of this additional term, detects this additional term, knows that it's proportional to the lensing potential, and makes an estimator of the lensing potential. All right. So there is only one or possibly two slides of algebra, and then we can wake up and say, okay, fine, whatever, there's some algebra. Okay? I'm going to do it whether it's okay or not. So, you can I only know how to make sense of this in this. It seems to be a kind of complication. So let's Fourier transform this relation t equals t plus this bit. So far so good. T transform is t transform plus the transform of this, which is this expression. Where does that come from? Each of these is to be thought of as a Fourier superposition. It's a sum of psi tilde times wave and sum of psi tilde of t tilde times some other wave. But we're interested in the gradients. And I'm sure you remember one important thing, which is that you take the gradient of some field, transform, you get I times the wave number times the field transform. Yes? Gradients become wave vectors with an I. All right, so we've got two of those. So there's a minus sign. We're converting the sum into an integral, so over 2 pi squared. And we take a dot product, so it's a dot product of two wave vectors. And there's a multiplication of that's the two Fourier space amplitudes. But there will be a restriction that the Fourier components of these two terms need to combine to make the Fourier component that we're interested in. So we want to get some wave number k. So these things have a wave number k1 and k2. So they need to add up to make k so that the exponential term is the wave that we're looking for. So it looks a lot more complicated than this. And it is, but funny enough, we will, having tumbled into Fourier space, there'll be a pile of Fourier manipulations using the kind of tools I went through. And they will end up out in real space.
Why would we integrate over K1 only, not over K?
Well, K is fixed, right? So it's the wave number that you're interested in. So you have this, which contains e to the ik1 times e to the ik2, which is the sum of those k's, and then you're multiplying by e to the minus ik an integrand. Okay, and so the delta function means that that k has to match the sum of those two terms. All right, so now we're at the crux. Because, remember, I said what this additional term is going to do is to introduce correlations in Fourier space, which, if the CMB is unaffected by lensing, would be absent. So this is what this stuff looks like. And again, first slide, you think, oh, right, it's not to be written any more simply. Well, all I can say is That was what I thought when I looked at the review articles. Well, these equations are about twice the length, so I try to simplify them as much as I can. But the basic content is fine, I think, because we're just going to take two of these terms, two different k's, so I make a copy of this equation, replacing wherever you see k, replace it by k prime, and we've got to stack them together. We're only going to work to linear order in the potentials, so the cross term between these two nasty bits doesn't appear. So what's interesting is t with itself and t with this integral. And so as far as the integral is concerned, this is a constant, because k is some fixed thing. So this will come inside and we'll get a t times a t. T with itself gives us, of course, the basic homogeneous relation. Battery's getting tired. So, okay, so here's the 2 pi squared times c. So in the CMB world, power spectra are called C and not P. I don't think it's C for CMB, but anyway, that's why it's a C and not a P. There's our delta function. And here are the other two terms that involve products of the t that was in the integral and the one that was outside. And I've taken an ensemble average because I want to see if there's going to be correlations apart from the delta function. So those come inside the integral. And because I'm working to first order the Lensing potential, I can just use the zero correlation, which is this thing, which is our from the delta function. So now we can use it to carry out the case-based integration. And you can use the fact that this thing involves the power spectrum. So now you can see that the ensemble average, the product of the two temperatures in Fourier space, is the zeroth order term plus a term that's proportional to the Lensing potential with some coefficients that depend on the two k's that you're interested in and the intrinsic correlations of those two k's. So the intrinsic power of those two k's. All right, so you might think we're almost there. We nearly are, because you can say, well, if I can invert it, if I know this is the thing that's ensemble average, so we can't measure it, but we can estimate it by replacing the ensemble average with the actual average over the data that we've got. So this is the ergodics term, ensemble average versus spatial average. So we can just, therefore, look for any off-diagonal term, k is not equal to k prime, divide by this figure, and we learn the Lensing potential. Yeah, we're done. Well, actually, it's too good, because we can do this for any value of k and any value of k prime. Each pair of wave vectors gives us a different estimate of the Lensing potential. So, what seems sensible then is to average all these possibilities in some way. So what I'm going to say is, this is a great piece of text thing, right? Psi tilde is what? It is the Fourier transform of the thing we're after, the Lensing potential. With a hat on it. And the hat, anytime you're doing something statistical, means this is an estimator of the thing I would like to know based on some finite data. And we've seen that psi tilde is proportional to the correlations in the temperature or in amplitudes. So we'll just take those, multiply them by some weight according to the wave vector, sorry, that I'm interested in a given value of weight vector with big K. I have estimates for all sorts of values of little k, which is the opposite in K space. So I weight them by some amount W, I don't know, integrate over K space to do the averaging. So if I knew the weight, I can end up with an estimator for Lensing potential in Fourier space, do a Fourier inversion, we've got a map done. So what is the weight? How do I get the weight? Well, again, this is a very common problem. You have this degree of freedom in some statistical problems. You want to find the best way of weighting. Best means most precise. Most precise in what? Well, most precise in terms of the fact that there's noise. So let's look at this thing. Whatever W is, it's going to give you an answer for some input temperature map, and that answer is going to be non-zero. So this is a fundamental problem with CMB lensing. Even if you have a perfect noise-free picture of the microwave sky, because the microwave background fluctuates, it will produce a fluctuating estimate of the lensing potential. Right? But on the other hand, we do know that the lensing potential should be obtained in ensemble average. That's how it's motivated. So if I take this top equation, take an ensemble average of it, I get the ensemble average of the 2-point function, which I got before, it's the sig involving the power spectra, times W. So what I can say is the expectation value of my estimator is the thing after the true value times some function of wave number, let's just call it A for shorthand, times the length. Okay, so strip this down, it just says expectation of my estimator is proportional to integral of A times W. Okay. What about the noise? Well, if we take the limit that lensing is very small, so we're actually dominated by what we get is dominated by the fluctuations, then the variance in our estimator is just the average square of the estimator. That's fine because we have our estimator here, so I can square it. So if I square this, I'm going to double integral, two wave numbers, A prime, and I'm going to have four t's, t prime, and another two copies involving, say, k prime. So those four t's can combine, pair of them, combine to give you a power spectrum in two different ways. So that's what gives you a factor 2 there. So when you do the ensemble average, that turns t into two TTs, which is few correlations, and it squares the window function. So the bottom line is okay. Well, the bottom line, nevertheless, is then some other function, wave number times the window function times the weighting squared. The thing to point out though, is that everything up till now, C has been the power spectrum of the microwave background. And actually show what it looks like. It's that, right? But that's not what you measure. You measure that plus some noise, which becomes dominant on small scales. It has to be statistically subtracted off from the Planck results. But when you look at the actual Planck map, then of course you're sensitive to that noise, whereas these predictions, that's the correlations, well, they're made before you've added noise to the map. So here, C means just this function without addition of small scale noise. And here, C has to be the total. In the future, as we will see, CMB maps are going to be so dominated by cosmic variance that this extra correction is negligible. But at the moment, it's really important. Okay, so I've got these two known functions, A and B, and I've got the weight that I don't know. So this is the last slide with maths. Yeah, there's time left. So my signal to noise then is the so this is the expected signal, the expectation of my estimator, and this is the variance of that signal. So the signal to noise squared is the square of this thing divided by this thing. Because in terms of notation I use, it's integral of A times W squared divided by integral of B times W squared, integrating over the wave. So how do you find the best W, the best weighting to optimize that signal to noise? The answer, if you're being fancy, is functional differentiation. But what it really means is you just say, let W become W plus delta W, expand the first order, and require that the change is zero, because then you've minimized, or you've optimized the signal to noise. And if you do that differentiation, you will find that W is just a ratio of these two functions, A over B. So we know what A over B is, because we have expressions for them. So there's our final estimate. It says it's the integral over product of observed Fourier coefficients in the temperature field, with star, which I'll stay more about in a second, times the ratio of these scale dependent factors divided by the ratio of A squared over B. And that is the bottom line. It's quite a neat expression. If I got that far, I'd say, great, I'm going to publish. I'm done. But you can make it better. You make it better by exploiting the property of all these things, which is that the temperature is real. It's a real field. That means that its Fourier transform is Hermitian. By which I mean that T tilde K is conjugated is equal to T tilde minus K. So you can get rid of the complex conjugates that are in here by using the Hermitian symmetry. And when you do that, you can boil this expression down to, okay, here's the normalization outside here, A and B, but the term inside can be expressed quite simply. A and B, as I had them, they involve dot products. And you'll notice that the wave vector that I'm interested in, K, is actually there in common. So in fact, it can be taken outside, leaving something else as a vector inside. So then the expression looks like K outside the integral, and there's a little K vector inside. Now you stare at that, and you think, whoa, I know that there's a ratio between gradients and powers of the wavelength. So this is saying that what I'm looking at, because it's got a wavelength here, has to be the Fourier transform, the divergence. It's K dot in Fourier space is the same as del dot in real space. What have I got inside? I've got another K, So similarly, there's also a gradient being taken. And finally, you say that this temperature times temperature hat offset, you recognize as the form of a convolution. You can involve two functions, it's like f of x times f of y minus x, or g of y minus x. So what I've got here on the right-hand side is actually a Fourier transform of a convolution, or rather, it's the Fourier transform of the divergence of the convolution. So in real space, it's the divergence of the product of two fields. This is the convolution theorem. Take two functions, multiply them, Fourier transform it, you get a convolution, and vice versa. So finally, the answer that we've been seeking is just incredibly simple. And I wish I could convince myself that obviously it's just this. I think it's a minor miracle we end up with. But that's why I went through this, because the final result is just incredibly beautiful. It just says you define two functions, f1 and f2, and both of them are your CMB map, perfectly filtered. And you express the filtering in Fourier space. The first one I divide by the total power spectrum. The second one I multiply by the ratio of the intrinsic to the total, which is intrinsic plus noise power spectrum. Then I take the gradient of f2, multiply by f1, and take the divergence of that whole shebang. That is a map of the Lensing potential, which, remember, obeys Poisson's equation, so I can invert Poisson's equation in Fourier space. And I've got a map of the Lensing convergence. All right, so that was a lot of work, but each individual step is just using these same sort of tools of ensemble averages, delta functions in Fourier space. And as I said, this sort of spade work is used in a lot of other contexts. And I think it was worth going through that. I hope it was. So we just pause here before we kind of go back to pretty picture land, see if there's any questions that you can sum up. And I'll say, okay, so we'll take trivia, we'll get on with it. Yeah? Okay, it's two of it.
Maybe not a question about these derivations, but in the very beginning where you showed us plot of the Lensing system, we have these two arms.
Yeah.
So there we have to remember that we are gauging this difference with respect to a straight line in some space. And so the source is very compact and the space is flat, and then the Lensing potential is really the Lensing potential. But if the light travels to a very extended object on the outside, then the straight line is a straight line in a polar region. So we have to subtract that so we don't come up with the wrong answer.
Yes, that's true. What I didn't say is that this would be called a thin gravitational lens. So, I mean, the deviation here is hugely exaggerated. I mean, what this, for example, the picture I showed you right at the start, where you can see the octopus sucking on the CMB sky, that would be the radius of that ring is this distance, and in practice, the biggest it can be is half the 1 arc minute. So this angle is really small. That's why even though the path is continuously curved, most of the bend angle only happens in a very small distance of the deviating object. Well, once it becomes large angle deviations, if you had a 10⁻⁻⁷ mass thing on the sky with a nice time ring radius of degrees, then yes, it'd be problematic. There's one there.
If you go back to the final expression, I got a bit confused with how it was written. Like, yeah. Yeah, so it's the gradient of the first factor multiplied by gradient of the second factor and all together, or
So, well, I've defined two versions of the temperature field. These are smoothed in various ways. Think of F2 first. When the wave number is small, this ratio is pretty well united. But eventually, when you get to high wave numbers, when things become noise dominated, this factor falls to zero. So there's a critical scale at which this is happening. So you're just knowing the temperature field a little bit. This one, you're dividing by the power. So wherever the true power in the CMB is large, you're reducing the signal, which kind of makes sense because the CMB has a loss of spike L of 220. And at those wave numbers, it's obviously going to be very difficult to pick up the lensing signal. Right? So you downweight field F1 in those sort of regions. And then having made those two fields, you just take the gradient of F2 and multiply it by F1, which overall makes a vector. You take the divergence of that vector, and that's the estimate of the lensing potential.
okay, I think yes, thank you. That really helped.
All right. Well, thank you for indulging in that. As I said, I'm really enthusiastic about how neat this is. You share some of that enthusiasm, but whether or not, I promise no more slides of this. Okay, trust me. So let's do some pretty pictures of what it's all about. I showed you a simulated small patch of the sky. So this is something now that's more realistic. This is kind of tens of degrees across. I'm familiar with this sort of thing from Planck. So that's the realization of the ideal CMB temperature. Now we put the best guess about foreground reconstruction. They're not very different, are they? I mean, if I'd swap these two pictures around, you'd have no idea that I've done so. Your eye can tell you that one is less, the other isn't. So it's interesting, therefore, that this still works and works spectacularly well. Notice the shift that you see, the rearranging the sky, hiding the sort of order arc limit. But what makes them work makes this reconstruction work is, first of all, that the microwave sky is very smooth, those sort of scales. And secondly, the shifts are coherent. You can see whole patches of the sky just moving together. So the small scale statistics that are given the patch temperature are modified in a way that is all deviations are going in the same sense. Anyway, the proof is in the pudding, as they say. So here it is. And so just summarizing, for those of you who've been asleep for the algebra, the observed temperature field is the temperature offset by the gradient of psi, which is roughly got a term, the dot product of the gradient of psi and the gradient of the temperature. And another way of thinking about this is that this means that the observed temperature field is going to be correlated with its gradient. And that's one way of half understanding why this divergence of T grand T is a sensible thing, because such a correlation wouldn't be present in the product CMB sky. A random phase distribution like the microwave background, there's no correlation between the field and its field gradients. If you see one, it's an indication that something odd is going on. So you can see that if you if you carry out the gradient, multiply by temperature, that's going to pull out this term. If you take the divergence, T times grad T, and that's going to be something that's going to be the loss generator term in delta web psi, which is proportional to the convergence kappa. So as soon as you see this additional T grad T correlation, the idea of taking this divergence has some justification, but how you can justify particular filtering of the temperature that needs to be done without all that manipulation, I do not know. Anyway, here's a test. This is a picture of the grayscale shows you the modulus of the reflection angle. So white here would be a few light minutes, and you can see it's coherent over this big patch. If you run the reconstruction algorithm, you get this, which is good, but also not perfect by any means. Or you can have this, which is much better. What is this? Well, this middle panel is all that I gave you in the preceding derivation, which is how to use the temperature field. But of course, not only the temperature, but also the polarization. So you can use it as a parallel analysis, which is algebraically much more messy than this gave you. So I'm sure you're really keen to see how that works. And it's the same philosophy of exploiting correlations that wouldn't be there intrinsically. And putting in the temperature and the polarization information really makes this reconstruction work spectacularly well. This is simulated data. Actually, this is better than Planck resolution. So this is covered. This in 2006. This is definitely very forward-looking. Whoa! Don't do that. So let me show you what it actually looks like when applied to real data. So we have this done for the best part of the decade, basically, but it's got considerably better because when Planck year one, that wasn't the full mission, so the small-scale data were quite heavily noise dominated. Secondly, in 2013, the analysis only used the reconstruction based on the temperature. Whereas in 2015, they used polarization as well. And you can see, I think, well, you can see two things when I blink between them. You can see that quite a lot of the hotspots and cold spots are common, but quite a lot aren't. So the picture that you're seeing obviously has a signal to noise of order unity. And that's nevertheless, so I've chosen to filter that. And that makes a map of convergence. And this is kappa. So it's stretched between plus or minus 5%. So and remember I said that Hank Hoekstra tends to see a typical galaxy distortion of 1%. This is bigger. Why is that? How is that? Well, that's because the microwave background is further away than the galaxies. It was something a weak shear. So you can see here a certain lens bend. The further away the source is, moves things further on the sky. Okay? So the lensing distortions in the microwave background are actually greater. One thing that helps. And between 2015 and today, okay, I was in the middle of saying that I've chosen to filter this map with the beam size of full departure of 2 degrees, which is big compared to the Planck resolution. Basically because on smaller scales, the noise is only pure noise. So you can see you're only learning about large-scale fluctuations. But large-scale fluctuations are great because they inhabit a linear regime where the perturbation theory is applicable. When I first saw this, I thought this was just amazing. Every blob represents some supercluster of galaxies or supercluster yet to be born, but the dark matter fluctuations that will generate it. And by the way, as we will show in the next segment of this, typically these signals are coming from stuff at redshift 2. So this is mapping out every supercluster ever existed between redshift beyond 2 and low redshift, putting them on a skewer, and presenting them up to you all in one go. It's everything that there is. It's all the structure there ever was in the universe. Right there for you to look at. And it's lucky enough that we can look at the intrinsic microwave sky and see the structure that existed in the universe at redshift of 1100. But to see everything that's happened in between, all done just courtesy of a few slides of Fourier transforms. And there's nothing short of miraculous. I think that would be a good point to stop. What I'm going to go on to next time is talking about how well, how precise these measurements are, and how well they agree with the cosmological model, how we can probe the cosmological model using this map, and what the outlook in this subject is going to be. But you worked hard. I know it's the end of the day. Thanks for not walking out when I try to go through the details, but I justify why that was, and no apologies. Right.
So now we can have some questions to the audience. Yeah.
Thank you so much. Sorry, I'm a little bit late for your lectures, but it's really interesting. I have two questions. First, it's now our resolution enough for detect this influence of the lensing, of the CMB lensing.
Yes. There are slides for my next lecture that will deal with this, but yes, next generation experiments will be better than Planck in 2 ways. Stop. Do that. Come on. Time here. Yes, thank you. I'm going to press the pointer. Okay, so Planck, how can Planck be improved? You can reduce the noise, the instrumental noise at small scales. You can also improve the resolution. So the Planck data have a beam of 4 bit maximum 6 arc minutes. Remember I said the typical sort of scale of these lensing deviations is a few arc minutes. So they're in danger of being convolved away by the Planck beam. It's just good enough resolution to see it. But something that has sub-arc resolution sees it with much greater signal to noise, especially as also these new generation experiments have negligible instrumental noise.
I mean, not about spectral resolution, about our accuracy in detecting the different temperature. Now, if I'm right, Planck can detect temperature up to 10 up -5. Yeah.
Yes, that's right. 100
Yes. So it's enough for doing this, or it's not correlated with
Well,
this?
the results, as I said, there are two things that influence this. The spatial resolution of that and the precision. And if you improved either of those, so if you reduce the instrumental noise or the resolution, then the signal noise and the lensing reconstruction becomes much better. Now, the next generation experiments will have map errors of like 10 microkelvin or 100. That's an order of magnitude in temperature, and the spatial resolution is an order of magnitude better. So that's why this field is going to undergo a revolution. but I'll show you some taste of the future next week.
Okay, thank you so much. And my another question. So we estimate our cosmological parameters from CMB. If we to take into account the lensing in the CMB, can it be possible that we obtain some changes in our cosmological parameters?
Yes. Again, so it will be the same answer. That is also what I'll be talking about in the next lecture.
Sorry,
But no, it's fine. The answer is interesting in that you can ask whether the statistics of this lensing map are they consistent with the standard cosmological model? Because Planck, as you say, right, from the intrinsic temperature fluctuations, we pin down the main cosmological parameters very precisely. We should be able to predict this map. And the question is, does it look as we would predict? Because if it doesn't, that opens the door to some new physics. So come tomorrow morning and see whether it does or does not.
Okay, thank you.
Thank you for an interesting lecture. I have one question. What objects would be detected through CMB lensing? Would it be primordial black holes?
No, the signal that we're seeing, I mean, it's okay. Actually, yes. So let me explain. Okay, that's not seeing quite. Oh, yeah, there it is. Good. My wallpaper happens to be a simulation of the large structure of the universe. What you see are dark matter halos, the most massive ones are 10 to the 15 solar masses, and in the voids it looks like there's nothing, but actually there's still some, even in here, the density of dark matter is perhaps 30% of the average of the universe. But it doesn't contain any dark matter halos that can be resolved at the limit of the simulation. Okay, so a lot of the signal that you see comes from the more massive halos, 10 to the 12, 13, 14, 15. But even if you took those away, about 30% of the signal would still come from these very unstructured regions of the universe. Those still contain dark matter, which you could more or less think of as basically lacking structure at all within the voids. So, but there would still be sensitivity to how much, as I said, about 30%. And so whatever it is, if it's primordial black holes, which is the fact you can string the possibility of still some windows, then they would be contributing. Obviously, you wouldn't detect. Remember, the first simulation I showed you was like looking at the CMB towards this thing. Then you saw an Einstein ring around it. Well, you're never going to detect it individually. You have other constraints on how big they could be. But in terms of the total constituents, sure, if you're just able to diagnose the total. This is the great thing about CMB lensing, one of the many great things. It's sensitive to the total mass of the universe. So it counts neutrinos, it counts the whole black holes together.
Excuse me, if it was not connected.
No, that's a good question.
Thank you for the amazing lecture. At the end of the lecture, you pointed out when you showed us the CMB fluctuation map that high temperatures, high fluctuations can somehow direct us towards clusters or superclusters of galaxies. So I just wanted to ask, because of the different kinds of anisotropies that are there in the CMB, is it okay for to say that higher the temperature, more the mass in that particular region?
No, not at all. Actually, have I did right at the start. Okay, so that's the intrinsic CMB. That's the thing that's being distorted by the lensing, but there's no, well, okay, you can actually, I have a better map. No, so you can look at that and you can say, well, pick a hotspot like there. This corresponds to some structure at redshift 1100. And you ask, well, how big is it? The answer is, you mentioned this later in subsequent lectures, but you've heard of baryon acoustic oscillations. So you know that's something we can measure in the galaxy distribution. It's a length scale acoustic horizon of about 100 megaparsecs. Well, that same length scale is already printed at our scale. And it accounts for these kind of 1 degree size plots. So the stuff you're looking at here or there, those are individual matter fluctuation enhancements of matter density, 500 megaparsecs across. So today, they're still in the linear regime. So you can't associate it with a single collapsed massive structure today.
I have another question. So, how exactly, because there are different kinds of anisotropies, and if we had to parameterize their magnitudes, so how do we do that in CMB? Like, for example, the primary anisotropies and secondary anisotropies. So, how exactly do we parameterize them?
Okay, well, I summarized that briefly in the first few slides. This unlens is an idealized realization of what you call the primary. And so that's from this map propagate to our line of sight and are influenced in various ways, introducing secondaries. So gravitational lensing is the prime one of interest. But on larger angular scales, as I said, there's the integrated Sachs-Wolf effect. On small angular scales, there's the Signal-Aldovich effect. So a real CMB map would have this at some random point, like there, you might see a little dark black dot, which would be a single pixel at the scale of this map. And that would tell you that at that location, somewhere on the line of sight, there was a cluster of galaxies with a hot intergalactic medium, and the plasma in that medium is compromising CMB photons. Okay, so there's some allowance has to be made for that foreground reducing primary fundamental cosmological constraints from the primary CMB. Thank you.
Thank you for your talk. What is the order of convergence we expect from CMB Lensing? Order of magnitude of convergence?
I showed you there it is. That's the actual Planck map. Most recent version, and it's stretched between convergence minus 5% and plus 5%.
More than weak lensing.
Yeah, exactly. And as I explained, that's because the microwave background is further away. And if I move this pointer, it doesn't do too much on my hand, but on the wall, the same deviation is larger. It's just that geometric lever means the CMB effect is bigger.
Thank you. So I don't know if you will cover it tomorrow, but can we in weak lensing it probes the total matter distribution, but in CMB lensing can we does it probe the dark matter distribution and dynamics separately, or
No, gravitational lensing, whether the target is just background galaxies, which is one, or the CMB, the good and the bad thing is that it just tells you the total gravitational deflection. So it's agnostic about whether that's due to dark matter or baryons. It's a combination of matters. But I would say that one of the good things about, as I'm sure I mentioned, one of the challenges that the galaxy faces is that energetic input from star formation moves the baryons in the real universe relative to the dark matter. It tends to expel gas into Hades. So the small scales, the small means order of megaparsec, the kind of mass distribution is interfered with in a way that's hard to model. So you'd rather stick clear of those scales and make measurements that are on tens, hundreds of megaparsecs. That's hard for galaxy lenses to do, but CMB lensing, once it's in the sky phenomenon, gives us much cleaner data in a linear regime.
thank you.
So we have time for a last quick question.
Yeah, go for it. Go for it.
It's very interesting. My question is, how you plan, I have planned how we can to take into account this effect of gravitational lensing, because on the image it's similar when we use the convolution algorithm for restoring our image due to distortion that our instruments are not perfect. So I have planned how you can take into account this lensing for restore real image of CMB distribution.
Yeah, that's very good. If this Kappa map was ideal, supposing somebody just gave you the true Kappa map, that allows you to predict the displacement vector at any point on the sky. So obviously you could then de-distort the temperature now, and you would recover the temperature in a way that's as if gravitational lensing never happened. Now that de-lensing, it's called, is very interesting. Basically, one of the ways in which the microwave background is very informative is through the polarization signal. I don't know how many of you have heard. Okay. Who's heard of CMB B modes? Okay, some have, some haven't. B modes is it's a term that stands for the signature of primordial gravitational waves, which have not been detected yet, but are our prediction in inflation. So if primordial gravitational waves exist, they produce a characteristic polarization pattern on the CMB sky. The trouble is, which without gravitational waves would be zero. The trouble is that gravitational lensing creates a fake pattern. So people detecting, trying to detect primordial gravitational waves hate lensing because it induces a B-mode signal that's not primordial. So what you would ideally like to be able to do is to de-lens the CMB sky. The other thing to mention, oops, is that, remember I said that, we're using this linear approximation for the change in the temperature, and there's plus quadratic corrections. And you might think, oh God, do I have to do all that algebra again, but Taylor expanding further, life is too short. But what you can do is you can iterate. So you just make a linear approximation, you estimate a map, you then de-lens the temperature for the according to the lensing potential you've estimated. And if that linear approximation wasn't correct, there will still be some further displacement. So you just iterate the same linear algorithm and you recover the second order term. So these are two excellent reasons for wanting to do de-lensing. Doesn't really work with Planck yet, but it will work very well with the future data sets.